Alright, and there we are. Hello, folks. How are you? Welcome to We Need Our Space Live, hosted by the Irene W. Pennington Planetarium. I'm also your host, Jay Lamb, planetarium producer and technical manager at the Irene W. Pennington Planetarium, housed in the lovely Louisiana Art and Science Museum. So, this is going to be the second show of today. The first one was at 12 o'clock. So we're going to cover the same ground here, the inner planets. But in this show, I'm going to cover a little bit more. I'm going to kind of expand a bit more from what I was talking about at the 12 o'clock hour. And then next week, we'll cover something completely different. So first things first, I must remember to minimize my window because you don't want to see me that much. There we go. That'll be fine. Okay, well, where are we going to begin today? We're going to begin right here in Baton Rouge, Louisiana. As you can tell, this is around 7 o'clock, so the sun is beginning to set just a tad. So what I'm going to do is I'm going to change time a little bit. Let's back up. There we go. Let's reverse time a little bit. That's better. Now we can see the Baton Rouge on the river. And with that, we can also scoot over just a tad until we see the Louisiana Art and Science Museum. I am not there right now. I am at my home office, but let's circle around to take a look at the Paper Clips dock where we are at. Now, this looks as though we are in some type of plane looking down. That is intentional because I'm going to flatten out our view so we can look across and see the horizon. And then we're going to travel across the Mississippi River before we go up into space. Traveling across the river because I want to illustrate something important here. So let's say you were at one of these houses down here. Let's see here. Let's see you're in this car. So you'd be about a pixel or two across, very small. So if you were looking out across the horizon as it appears right now, you would see what appears to be a flat horizon. Well, the Earth is about 8,000 miles in diameter. So as we lift off from the ground and travel the many miles it takes for us to leave the atmosphere, we will begin to see what that 8,000 miles really looks like. The farther we get up into space, and that blue haze of the horizon, that blue haze of the atmosphere goes away, and the blackness of space comes in, we can now pull away from our planet Earth and see how that curvature of the Earth comes into play. We can see that great blue marble that it looks like up on high. As I pull out, the information that I'm getting here is being pulled in from real time on the internet. So there's clouds, the atmosphere, the imagery that you see is being pulled in real time. I'm just going to try to reorient myself here to align myself with the orbital lines of the other planets. Because now we have left planet Earth, and we can see a couple of things now. Check one thing. We can see this orange line here that represents the rotation of the Earth. And then we can see this blue line that represents the orbit that the Earth takes around the Sun. And then these other lines behind the Earth that represent the other planets in our solar system. So to start off with, we're not going to hang around Earth too long. We are going to go out and we are going to see Mercury, the very first planet in our solar system, little tiny Mercury. So let's plot a course to that planet. I'm going to keep these orbital lines up because it kind of helps us see how fast we're traveling and where we're at. If I turn them off like that, it makes it very difficult to see where we're at. And now we can see what we are approaching. We are approaching Mercury. Now, whenever we get this close to Mercury, what does it look like to you? It looks a lot like our own moon. Well, I'll get into that in a second, because as I have approached Mercury, now that detail is coming in. It's downloading, and now we can see the surface of Mercury in fine detail. First, let's talk a little bit about the origin of the planets here. So in the beginning of our solar system, tens of millions of years ago, gravity drew the gas and the dust together before there were any planets. This is called a protoplanetary disk. The rocks and the debris that was in our solar system coalesced by gravity. And the worlds began to take shape as any shape wants to take in space, to the form of spheres. This protoplanetary disk we'll talk about again right towards the end. But over billions of years, we then got the planets. So here we are at Mercury, some 36 million miles from the Sun. So you can see the craters here along the surface. It may remind you of the Moon, since both the Moon and Mercury lack an atmosphere. So there's nothing to stop these worlds from being bombarded by meteors and comets. Mercury also has a very slow rotation. It's so close to the Sun. Now, since it's so close, it's almost gravitationally locked to the Sun, much like our Moon is gravitationally locked to us. So if you were able to stand on the surface of Mercury, you'd have to go around the Sun twice to experience one full day. So a day on Mercury lasts 176 Earth days, whereas a year on Mercury takes just 87.9 Earth days to complete. Mercury is also the most metal planet of all. It has a huge metal core with just a little bit of rock surrounding that. Let's get in a little bit closer to Mercury. The images you see here are actually images of the surface of Mercury, thanks to the Messenger spacecraft that had orbited Mercury since 2011. As you can see, as I get closer, we get some finer detail. So Mercury was orbiting, Messenger was orbiting Mercury since 2011. In 2015, its mission was complete, so it crashed into the surface of Mercury, leaving yet another crater. Now, just because Mercury is so close to the Sun, it doesn't mean that it is the hottest planet of all. In fact, we'll get into the hottest planet in just a moment. I just want to show you the detail here in the surface of Mercury. Really, if you've seen one area, you've pretty much seen it all. Some craters are much larger than others, and some are very, very small. Let's go ahead and leave Mercury. We have some more interesting planets to look at. Let's go to Venus now. Come on, Venus. There you go. Here we are approaching Venus. We see that orbit line right there. Here we are. Well, Venus is very bright in our nighttime sky. In fact, right now, if you do leave, not just yet because you're watching this, but if you do leave the house and you look over to the west, you will see a very bright object in your sky. That is going to be Mercury. Now, why is Mercury so bright? Well, whenever we first laid our eyes on Venus, I'm sorry, I said Mercury, not Venus. Well, whenever we first laid our eyes on Venus, we could see that it was covered with these thick clouds and a very thick atmosphere. This made it impossible for us to see past the clouds into the surface. We didn't know what to expect. So in sending spacecraft there, we didn't know what to make. The thick layer of clouds of Venus is why it is so bright. In fact, here is an image of those thick clouds. So we didn't know what the surface quite looked like. But these clouds and this atmosphere of Venus reflects the sun's light quite efficiently. In fact, here's an image I took of downtown Baton Rouge, right on the Mississippi River levee. You'll see that little park bench there with no one there. Right above that is the moon. some 238,000 miles away, still pretty bright. And right above that, you'll see that bright dot. That is Venus. The moon is 238,000 miles away. Venus is 67 million miles away. So it's still very, very bright. In fact, here's another image of Venus from the backyard of my house. Right there, right as the clouds were breaking, I saw Venus. Again, you can see this for yourself. This was a long exposure image, but you can go out and see Venus very clearly for yourself with a naked eye. No need for long exposure, no need for telescopes. It's right there for you to find on your own. Well, we see the surface of Venus right now, peering through the clouds thanks to radar technology, thanks to the Magellan probe. Thanks to the Magellan probe, we were able to map the surface. Now, back in the early days, we didn't know what lay beneath those clouds. They thought it was a very swampy planet, a very marshy planet. In fact, this is why the Soviets designed this. This is the Venera 4 probe. They had this Venera program to explore Venus, the Soviets. So when they made the Venera 4 probe in 1967, they made it into a sphere because they thought that it was going to splash down on the surface. So they made it into a splashdown module. But the Venera 4 probe didn't quite make it. In fact, the Soviets sent out 8 Venera probes. Each one of those failed. It wasn't until Venera 9 and 10 that we were able to get close-up black and white images of the surface of Venus for the first time. It wasn't until Venera 13 that we were able to get the first color photo of Venus. Now, Venera 13 was made so that it could withstand the pressures that could even crush a car. It also could withstand, it had to withstand heat that could even melt lead. The surface of Venus is quite hot. So it had to endure temperatures upwards of 855 degrees Fahrenheit. So it didn't last long. It lasted about 127 minutes on the surface before it succumbed to those high temperatures. It is believed that early on Venus and the Earth were very much alike. That both Venus and Earth had rivers and seas. What happened was the sun got warmer. And as the sun got warmer, Venus began to heat up. So over 2 billion years, the sun's intensifying heat evaporated the water into vapor. So the vapor combined with volcanic gases, and this created a very volatile cloud system around the planet. So in 1990, NASA's Magellan probe, equipped with cloud-penetrating radar, was able to peer through the atmosphere of Venus and discover lava plains, lava domes, and even some shield volcanoes. We're actually going to go visit this in one moment. Maxwell Montes, the biggest, the tallest mountain on Venus. Discovered some lava basins as well. Well, also on Venus, I mentioned those clouds. Well, Venus has sulfuric acid clouds, which rains sulfuric acid. Sounds kind of like a nightmare, actually. Sulfuric acid on Earth is used to clean out drains, to dissolve hair, to dissolve grease in drains. It's very volatile. Well, these greenhouse gases trap the sun's heat. This is what makes Venus so hot, and this is why Venus is the hottest planet in our solar system. So as I promised, we're going to visit that mountain. It's right over here, just below that northern pole of Venus, right there, that little bright white spot. Let's zoom in. Now you probably notice these little striations here along the surface of Venus. Well, that is not alien landing strips. That is actually going to be some missing data from the Magellan probe as it was orbiting. Let's rotate around just a little bit here. Let's zoom in here. Let's let that data kind of pipe in just a tad so we can get some higher detail. Now, As we get closer, we will begin to see that this is a very tall mountain. It's about 7 miles at its highest peak. The diameter is around 495 miles. Now this bright area here, you might think that that is the polar region, that it's ice. But actually, it is believed to be radar reflective pyrite. You probably noticed this dark area right there. So let's get in close to this. Let's get in around 200 kilometers, about 120 miles from the surface. With this dark circular region here, you'll see it's dark there, not as dark right there, then it gets pretty bright. This dark circular region you see is called Cleopatra. It is an impact basin about 62 miles in diameter. Now first, it was thought to be the remains of a volcano, but new research indicates that it was formed from a meteorite impact. So the dark center region there is fine dust, while this outer ring here is the ejected debris from the initial impact. It's thought to have been formed a few centuries ago. So Venus is not a place we would really want to travel on a manned mission. Let's go ahead and back out a little bit from Venus. Venus is considered the Earth's sister planet because they're both very similar in size and they both are composed of very similar materials. Now I'm going to just square us up. I like symmetry, so I'm just going to square us up here to the orbits. Now let's go back to Earth for a brief spell here. Now we're not going to spend too much time at Earth. I already know a lot about that. Let's go back to Earth because we are on our way to Mars. Here we are approaching Earth. We will see that moon 238,000 miles away. As we approach Earth, we will see the orbital path of the moon. As we get closer, we'll see those clouds there. So it is because of the Earth's size and its position in the solar system, it was not only able to host water, but to keep water. So Earth's size enables it to keep its atmosphere and to keep it stable. So protecting the water, which enables life. Now what I'm going to do now is I'm going to get closer to the Earth to take a look at this atmosphere. Let's see, let's go on this side here. Let's see. Rotate around here right from that little rotation path. That looks nice. Okay. There we go. Missing data there. That's alright. Get away from that. Better. Well, we can see this blue haze of the atmosphere there. Now let's just say I took away the atmosphere. Well, it would look like this. So let's rotate around and we'll see how Australia looks without any atmosphere. Where is it with and without? Let's see that data gets piped in. So the atmosphere, I'll turn it back on, is a mixture of nitrogen, oxygen, and small amounts of argon, carbon dioxide, water vapor, and other gases. But this protects us. It protects us by absorbing the ultraviolet light from the sun and reducing the temperature extremes between night and day. Now the reason why our planet doesn't look like Mercury and Mars is all because of this atmosphere. It protects us from meteor strikes. So the atmosphere protects us from meteoroid strikes because once a meteoroid hits our atmosphere, it's traveling extremely fast. It's so fast that the air in front of the meteor doesn't have time to actually move out of the way. So the air heats up from friction. Then the air is being forced into the cracks of the meteor, and then this begins to break pieces of that meteor off. So there's also there's a huge difference between the high pressure air in front of the meteor and the vacuum of air behind it. So most meteors burn up in the atmosphere. This is like a meteor shower here. So whenever they hit our atmosphere, they usually burn up, break into pieces, and then those smaller pieces burn up. However, some of those do survive and hit the ground with sometimes the impact of a very small nuclear explosion. So that's why our atmosphere is very important to us. One of many reasons. Let's bring Earth around here. Well, let's go ahead and head over to Mercury. We just went to Mercury, so let's go to Mars. Got Mercury on the brain. Here we are, approaching Mars, and as we get closer, we will see those two orbital lines of the two moons of Mars, Phobos and Deimos. As we get closer, this is almost just where I want to be. Right there. Okay, that's precisely where I wanted to end up. Mars is 142 million miles from the Sun. Some 4 billion years ago, Mars and Earth were probably very similar. So this is an image from Viking 1, the first color photo of Mars, taken on July 21st, 1976, 10 days before my birthday. Well, Viking 1 also, actually before I get into that, you'll see this reddish surface there. Now, the reddish surface of Mars is due to the high iron oxide on its surface. If iron oxide sounds familiar, that is what causes, that is the discoloration within rust. So when you have a rusty blade, a rusty piece of metal, that is due to the iron oxide. That is why Mars has that rusty, dusty color. This image is courtesy of the Viking 1 spacecraft. Well, also, Viking 1 took this image of the infamous face on Mars. You'll see right there, I'm circling with my mouse cursor there. You can see 2 eyes, a nose, and a mouth. So a lot of this elicited a lot of conspiracy theories. People thought that this was an ancient civilization that carved this into a rock, much like Mount Rushmore. But actually, it is not so. This was in 1976 when imaging wasn't really all that great. Well, we did get some better images, specifically in 1998. 1998, the Mars Global Surveyor captured a better image, the one that you see in your middle there. Now again, in 2001, the Mars Global Surveyor took an even better image. So you'll see that these little ridges here are kind of popping up, and this is casting a shadow which creates the illusion of an eyes and a mouth. Actually, in 2001, we saw that this was not a face at all, but actually a natural formation, sort of like a mesa. In fact, here is a 3D image of, actually that's a close-up image, and that is a 3D representation, a little bit lower to the ground so that you can really see what that supposed face looked like. Well, here we are back at Mars. Well, Spirit and Opportunity have also been taking some amazing photos. Now, Spirit and Opportunity are 2 rovers that landed on opposite sides of Mars in 2004. They've been sending back some amazing pictures. They both look very similar. Spirit and Opportunity on Mars, still operational actually to this day. So this image here, it's a photo that shows Opportunity. You see these little tracks there? That is the tracks of Opportunity. The rover was looking back towards part of the west rim of the Endeavour crater. Now that rover drove along, heading southward during the summer of 2014. Actual images of the surface of Mars. The Spirit and Opportunity also both captured many dust devils. You'll see a dust devil right up there. So they captured many images of these dust devils in their exploration as well. Just as on Earth, a dust devil is created by a rising, rotating column of hot air. When the column whirls, it is created by a rising column of hot air. And when the column whirls fast enough, it picks up these tiny grains of dust from the ground, making the vortex visible. Spirit and Opportunity also discovered plenty of signs of liquid water. Liquid water that once flowed across or percolated through the Martian surface long ago. Opportunity found some of the most convincing evidence late in 2011. This thin, bright vein of gypsum that was deposited by lake water billions of years ago along the rim of the Endeavour crater. At one point, it is believed that Mars also had rivers and seas and a decent atmosphere. Now, Mars has a very small core, and also has much weaker gravity than Earth. So it had a very hard time holding on to its atmosphere. This made it very susceptible for solar bombardment. Eventually, Mars, its atmosphere, was lost and evaporated out into space. So it still has a very weak atmosphere, which it can hold on to, but this is a representation of what Mars might have looked like some 4 billion years ago with water on its surface. Now there is some ice crystals, some ice water located around the pole region, but as far as flowing liquid water, it is no more. Well, currently, the Mars Reconnaissance Orbiter has made over 60,000 orbits around Mars, capturing the majority of the surface in detail and high resolution. It's captured these polar avalanches. This is a high-up view of this polar avalanches. You had a much larger picture here of these polar avalanches. It also has these shifting sand dunes, again an actual image from Mars of these shifting sand dunes, and these seasonal sand flows. Now when we first saw these, we thought that they were flowing water, but now we believe that this is just seasonal sand flows. Mars also has two very distinct, very notable geological features. So now I'm going to get a little closer here to this nice discoloration you see here. I'm going to zoom in on this. Now as I zoom in, I'm going to get some more detail. I'm going to remove the atmosphere of Mars. So you can see this a little closer. Let's take a little while for that data to come in. Well, this is Olympus Mons, or Mount Olympus. It is a shield volcano and the largest volcano / mountain in the solar system. It's actually a dormant volcano right now, but now it is the largest mountain in the entire solar system. So its size is almost that of Arizona. I'm trying to force the data to come in. It's not really wanting to. Back away a little bit here. So this, there we go, is about the size of Arizona. In fact, if you took two of our state of Louisianas, you could put a Louisiana right here, a little boot shape like that, and then an upside down Louisiana right there. So it's big enough to put two Louisianas up on its surface. Over here. So let's change our point of view for a second. Now this is not a three-dimensional map, but we can kind of get a perspective here. So, if you were to go to Olympus Mons and stand right here, anywhere along the rim of Mount Olympus, Olympus Mons, your entire horizon will be taken up by this mountain. Now it's easy to find Olympus Mons because it is right next to 3 other volcanoes. There we go. You see them right there, these 3. Scrius Mons, you have Pavonis Mons, and you have Argia Mons. And if we keep rotating around, we will see this, Valles Marineris. Getting a little dark here, so let's change the time. Oops, wrong time. Let's reverse time a bit more. There we go. Now we can see a little bit better. This is Valles Marineris. This is a deep, huge canyon on the surface of Mars. This is 2,500 miles long, 23,000 feet deep. This is so wide it could almost fit inside the entire United States. So wide it could fit inside Australia. So I want to take a little bit of a ride through Valles Marineris here. So I am going to change our perspective a little bit. I'm going to get rid of these orbit lines. we go. Let's get down low, close here. All right, now we're talking. All right. Here we go. So now I am going to turn the atmosphere back on. So there we go. Now we can see some detail there. So let's turn the atmosphere back on. Ah, that's nice. Take a little trip here through Valles Marineris. Now, there have been some theories about what created Valles Marineris. Some believe that this deep gash is due to something huge scraping across the surface of Mars back in the early stages of Mars's development. Some believe that this was actually a crack whenever Mars was first formed and it was cooling down, that this was created during the cooling down process back billions of years ago when Mars was first forming. All right. Just like going through Valles Marineris there. Let's go ahead and pull away from Valles Marineris. Alright. Because Mars has two moons that we can talk about. We saw them as we approached Phobos and Deimos. I really don't like when the orbit lines don't line up. I like symmetry. Okay, there we go. Let's look at these. Here we go. Let's just look at those moons for a second. Two moons, thought to be two captured asteroids, Phobos and Deimos. Phobos on the left, Deimos over here on the right. Now, Phobos means fear or panic. So think about phobia. It's named after the Greek god Phobos, who was the son of Ares, and is the personification of fear. Now, Deimos over here on the right means flight. Deimos was the Greek twin brother to Phobos. It is believed that Phobos one day will either crash into, gradually spiral into and crash into the surface of Mars, or will be attracted to Mars more, and then the gravity of Mars will eventually bust it up and sort of break it apart, and then Mars will then have a sort of faint ring system around it. But that won't happen for another 50 million years. So as I pull away from Mars, it is important to note that Mars is the only planet that we know of that is completely inhabited by robots. Now that we have left Mars, that is the last inner planet, but we are not quite done. We have some interesting things to cover for extra stuff. I'm going to center my interest on the Sun. Now, this is not a true representation of the Sun. If we were traveling to the Sun, we would not see this. But I want to center on the Sun to gradually leave the solar system. Now, it is said in some 4 to 5 billion years, let's get out here, some 4 to 5 billion years, the Sun is going to enlarge itself into a red giant star. Now, this is going to happen because the Sun is going to consume all of the hydrogen that is surrounding the core and all of the hydrogen inside the core. And then it will be forced to consume helium. So when it consumes the helium, it will then balloon into the size of a red giant star. And when that happens, the Sun is going to consume Mercury and the orbital path of Mercury. It will then consume Venus and the path of Venus. It will then even get close to Earth, as we see here, and completely consume the Earth. Some say it will get right up to the Earth. Some say it will get way out to the orbit of Mars. But this will not happen for another 4 to 5 billion years. If we are still around in that time, we have some time to figure out what we're going to do. So yes, Mercury, Venus, Earth, Mars. This little sun there, this little yellow star will become a red giant that will come out to the orbit of Mars. What are we going to do at that point? Well, once we have a red giant in our solar system, could be that the other moons or certain moons in the solar system could wake up and become habitable. Now, there are 3 moons worth noting. Europa, which is a moon of Jupiter, Enceladus, which is a moon of Saturn, and Titan, another moon of Saturn. So since we're talking about that, let's go ahead and visit a couple of those. Let's visit all of those to take a look at what they look like in person. So what was the first one I mentioned? Europa. Zero in on Europa, travel to Jupiter to see this moon here. We will cover Jupiter in better detail at another time. Right now, we're going to circle around to see it on its sunlit side. Let's get into Europa. There we go. Looks like a huge snowball. There is Europa. Now, the Europa is the smallest of the 4 Galilean moons orbiting Jupiter. The 6th closest to the planet of all the 79 known moons of Jupiter. We only have 1. Jupiter has 79 known moons. It was first discovered by Galileo Galilei in 1610. Now the surface of Europa. Surface of Europa, you can see right here. You'll see these bluish-white areas and these reddish and these yellowish areas. The blue-white terrain, now this is a sort of a colored picture, but the bluish-whitish areas there, that represents relatively pure water ice. Now these reddish areas, that represents ice and water ice mixed with hydrated salts. Now this leads us to believe that there is an ocean underneath this icy layer. An ocean that is about 60 miles deep. So that contains more water even than on planet Earth. So let's leave Europa here. Now we also talked about Enceladus. One of the moons of Saturn. Let's focus our attention on Enceladus. Let's leave Jupiter. Of course, we are traveling faster than the speed of light to get to these places in mere seconds. As we approach Saturn, we will see those beautiful rings of Saturn. Actually, while I'm out here, I should note that, in case you didn't know, the rings of Saturn are not solid. There's nowhere to land. They're actually composed of billions of particles of ice, and dirt, and dust. Some as small as a grain of sand, some of those are as large as a school bus or a house. Now, since so much of it is composed of ice, that is why these rings are so reflective and so easy to see. All the planets in our outer planets, Jupiter, Saturn, Uranus, Neptune, they all have rings, but Saturn has the most prominent ring system. Here we are approaching Europa, the smallest of the 4 Galilean moons. I said Galilean moons. Actually, that was Europa. This is Enceladus. Enceladus, again, it looks like a big, huge snowball. The 6th largest moon of Saturn is also composed of pretty much fresh, clean ice. It's an orbit around here. Now, the Cassini spacecraft revealed that Enceladus may have an ocean of salty water beneath its frozen surface. In fact, it has these ice geysers. These ice geysers routinely spew icy water and simple organic chemicals hundreds of miles out into space. And then there is Titan. Let's head over to Titan now. Titan is going to be much more interesting to talk about. As we whip around here to Titan, you'll see these dark areas there. We'll talk about that in 1 second. Now, Titan is interesting. Titan has an atmosphere, which is strange for a moon. But Titan is the 2nd largest moon in the solar system. It's even larger than Mercury. It has an atmosphere as well. Now, we sent a probe to investigate the Titan surface via the Cassini spacecraft and the Huygens probe in 2005. So it was designed to survive through Titan's atmosphere. It was the first time we landed on anything in the outer solar system. So right now I'm going to play a video of that actual landing. I'm going to mute my mic here so that we can enjoy a really cool video. Give me 1 second. That is pretty incredible. Watch this little parachute shadow up here. It's pretty impressive that we could send a spacecraft to videotape its descent on the surface. So you see these dark regions here. And Titan saw these bright highlands and these drainage channels. So there appears to be something flowing on Titan. It's not water. It's believed that Titan has liquid methane flowing on its surface. In fact, they think it has methane lakes, liquid methane lakes. So you have Ontario Lacus, Ligeia Mare, and Kraken Mare. Now, Kraken Mare is 5 times larger than Lake Superior. This is even bigger than the Caspian Sea. It's even bigger than the entire country of Japan. So the question is, what would it be like to swim in a methane lake? How different is swimming in a methane lake as opposed to swimming in water? The difference is, swimming on Earth is very easy because humans aren't as dense as water. Whenever we swim, we weigh less than the amount of water that we displace. The force of the water pushing back on us helps keep us afloat. Now in Titan, the lakes on Titan, your body would be much more dense than the liquid methane. So it'd feel like you were actually made of stone. So not only would swimming be hard, but we'd need a spacesuit that could withstand the negative 289 degrees Fahrenheit temperature and the very deadly levels of nitrogen gas, and get this, gasoline-like rains. So Titan also only receives 1% of the sun's light. So not a great day at the beach. You couldn't suntan, you couldn't relax. It'd be a terrible day at the beach. So let's get out of here, let's get out of Titan. Sounds like a terrible day because there are a few other things. Now we've covered the inner planets, we've covered some potentially habitable planets one day. I'm going to show you something else as a bonus that I think is pretty cool. I'm going to focus our attention on the sun once again. And there we see those orbital lines of Mercury, Venus, Earth, Mars. We see the orbital paths of Jupiter, Saturn, Uranus, Neptune. We are leaving our solar system. We see, where's Pluto? There's little Pluto right there. We're going to pull out a little bit further. And now that we are out here, I'm going to pull up. This is exactly where I wanted to be. How lucky for me. going to pull up some constellation lines. Constellation lines. There we go. The very familiar constellations. Well, you can see Orion, the very easily recognizable Orion with its 3 stars in his belt. Betelgeuse and Bellatrix in his shoulder stars. And then right, let's move this way. And then you can see his hunting hound Canis Major. Now that bright object right there, that is Sirius. Star Sirius. 8.6 light years away from us. So the reason why I pulled us out here is because I want to illustrate and demonstrate to you how space is 3-dimensional. It's easy for us to look at the stars up above, the sky up above, and get this idea that it's almost like a 2D space. Like the sky is a dark veil and the stars are these holes punched in the veil. But actually space is 3-dimensional. Some of the stars are closer to us, some of them are much further away. But we've made these imaginary figures in the sky. Many years ago, the ancient people saw these and devised the ancient constellation, the 88 officially recognized constellations. So what I'm going to do is I'm going to back away. I'm going to keep backing away from our solar system, and we can see how the close stars to us appear to recede first, and then the stars that are further away will then recede much slower. So think if you were leaving your house, you would see the stop signs and all the street signs going by very quickly, where the trees further away from you to your left and right appear to recede much slower. So let's back away from our solar system. Pay close attention to Sirius right there, Betelgeuse and Bellatrix over there, and watch how these stars slowly get pulled out of their constellations and how the constellations begin to warp as we leave our solar system behind. You can see these constellation lines are now warping, completely unrecognizable. It's to the point where I get right here, the system almost crashes. Come on, buddy. There we go. So let's keep moving out until we see how all the constellation lines, all the stars that make up those constellations, where they really reside. Now this one is so far away from us. And let's orbit around just a tad. See our place in the Milky Way. Let's go back because I wanted to show you. Let's go back really quick until those constellation lines reform, because there's 2 other things I want to pull up. One of them, I'm going to bring down the constellations for a second. One of them is going to be something called the Oort cloud, the Oort sphere. I prefer the Oort cloud. So what this imaginary sphere is, this is the gravitational limitation of our sun. It's also the boundary of the long-range comets. So anything that sort of comes through this sphere will be influenced by the sun. So let's say if a comet or something coming this way, it goes through the sphere, it'll be kind of arced that way. So this is the gravitational limitation of our sun. Its origin is said to originate during the protoplanetary disk we just saw. That was one of the first things we saw, the protoplanetary disk. All the debris that was left over from that protoplanetary disk coalesced closer to the sun. But whenever the larger gas giants formed, all that debris was sort of thrown out of the solar system. So it is believed that this is around 3 light years out. So I'm going to keep pulling away. Another reason why I brought this up is because it's also a great marker for where we are. I can't really see our sun right now. Really can't see it the further we go out. But I'm going to bring up one more imaginary object called the radiosphere. Another reason why I brought up the Oort sphere. Radiosphere, much larger than the Oort cloud. Well, this imaginary object represents the path, or the boundary, the limit that our radio signals have reached. So we've been broadcasting radio signals for about 100 years, since the time of Marconi. We've been really broadcasting since the time of World War II. So, about 100 years. So this is 100 years in that direction, 100 years in that direction. So it is 200 light years in diameter. So what I'm going to pull up right now is something called the exoplanets. Now, what does this represent? These circles are circles around stars that we know have at least one planet. Not one habitable planet, but just at least one planet. It could be a very small rocky planet. It could be a huge gas giant. The reason why I bring this up is because let's go back into the radiosphere. And now we can see, now that we're inside the radiosphere, we can see all the stars with all the planets that have been washed over with our radio signals. Whenever we pull out of the radiosphere, we can see all the planets that have yet to receive our radio signals. Now, the first exoplanet was first discovered around 1992. You'll see this one path here. People were really concentrating their telescopes into the sky in this direction. First exoplanet was discovered in 1992. And so far, there are around 4,000 exoplanets that we know of. Well, with that, I am going to conclude, and we are going to go back into our solar system and back to planet Earth. So to do that, I'm going to turn off our Oort cloud, our radiosphere, and our exoplanets. And I'm going to center ourselves on the Earth, and I'm going to show you how to find Baton Rouge. If one day you have your own spaceship, you want to go back home, and you want to find Baton Rouge, I'll show you how to do it. Here's our sun. Hey, buddy. All right. Here we are approaching outer gas giants, approaching our Earth. There goes Mars. There's our moon. Let's rotate around, and that is exactly where I want to be. Well, here we are in our spaceship, back at planet Earth, but now we want to go home. First thing we have to do is find the continent that you live on. That's going to be, for me, North America. We can easily find Mexico, and we can easily see Florida right there. And then right in between Mexico and Florida, you will see the boot shape of Louisiana. Here we go. Let's go in slow so the data can get piped in. Alright, well, once you've found Louisiana, there's Mexico, there's Florida, here's Louisiana, you can easily find Lake Pontchartrain. Very huge lake you'll see right there, that Lake Pontchartrain. As I get closer to it, I should point out that from this view, this is struggling. From this view, come on, buddy, we can see that straight line. That is the Lake Pontchartrain Causeway, which is the longest continuous bridge over water in the world. You can see it from here. You can even zoom into it and see the cars in it. I'm not going to do that right now. So you find Lake Pontchartrain, and then over here to your left, you will see the Mississippi River. And you'll see these squiggles over here at the top, these squiggles down there, and then this almost straight path right there. And then if you're really looking close, you can see in that river this little black line. That is the quote-unquote new bridge that we call it in Baton Rouge. So that's what you want to focus on. That one little straight path there. And then get down right here. And you can see that bridge coming into view. And then from there you will see the USS Kidd. And I can see the Paperclips dock. Bring it down here a bit more. Waiting for that data to load in. There you go, buddy. There's the USS Kidd. There is the Paperclips dock. Take a drink of my beverage here. And there we have it. We are back home easy, easy to fly through space. There is the old state capitol. There is our Art and Science Museum. And let's go back to where we started from. Right here in Baton Rouge. Well, hope you enjoyed that little tour of our solar system, some of the moons beyond our inner planets, and even beyond that. So, with that, I hope you have a good rest of your night. Be excellent to each other, and I'm going to leave some music playing for you so you can enjoy for a couple minutes. Good night, and I will see you next week with another program where we explore the outer planets, and then we're going to go even further beyond the radiosphere. So, until then, see you later.